On July 12, 2022, the James Webb Space Telescope released its first image of the deep universe. The plan was straightforward: look further back in time than any telescope ever had, confirm the timeline cosmologists had spent decades constructing, and fill in the remaining gaps. Webb was the most powerful space telescope ever built. The model was the most tested framework in the history of cosmology. This was supposed to be confirmation. Instead, almost immediately, the image broke something. In a patch of sky no larger than a grain of sand, held at arm's length, Webb found galaxies that should not exist. Fully formed, chemically mature, containing as much stellar mass as a modern galaxy, at a point in cosmic history so early that according to everything we understand about how galaxies form, there had not been enough time to build them. Not slightly ahead of schedule, impossibly ahead of schedule. The model that cosmologists had relied on for decades, the framework that successfully explained the structure of the universe, the afterglow of the Big Bang, and the distribution of matter across space, began producing the wrong answers. And the more Webb looked, the worse the mismatch became. The debate now happening inside cosmology is not a minor technical disagreement. Some researchers believe something unknown is hiding inside the physics of early galaxy formation. Others think the earliest moments of the universe behaved in ways our models never accounted for, and some are exploring explanations that go further still, ideas that reach beyond the edges of what we can observe, toward possibilities that most scientists have spent their careers treating as untestable. The telescope did what it was built to do. It looked as far back as physics allows. What it found there was not what the universe was supposed to look like. Tonight, we go through what Webb actually detected, why it matters, and what the leading explanations are, including the ones that most people are not yet ready to take seriously. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. The story begins with the model humanity thought it could trust. For most of human history, the night sky looked eternal. The stars appeared fixed, silent, and unchanging above us. But during the 20th century, astronomers realized the universe was moving, not objects within it alone, the structure of space itself. In 1929, Edwin Hubble published measurements showing that distant galaxies were receding from Earth. The farther away a galaxy appeared, the faster it moved. This effect came from redshift, the stretching of light as space expands across immense distances. It revealed something extraordinary. The universe was not static, it was growing larger in every direction at once. That discovery transformed cosmology. If space is expanding today, then earlier in time the universe must have been smaller, denser, and hotter. Follow the expansion backward far enough, and everything converges toward an origin nearly 13.8 billion years ago. The Big Bang was not an explosion inside empty space. It was the expansion of space itself from an unimaginably dense beginning. Evidence continued accumulating across the decades. In 1965, engineers Arno Penzias and Robert Wilson detected faint microwave noise coming equally from every direction in the sky. They had accidentally discovered the cosmic microwave background, often shortened to CMB, the cooled thermal afterglow of the early universe. Even now, all of space carries this ancient radiation at a temperature of roughly 2.7 Kelvin, only slightly above absolute zero. The universe remembered its beginning. Out of these observations emerged a framework called lambda-cold dark matter, usually written as Lambda-CDM. Over 50 years, it became the standard model of cosmology. Lambda represented dark energy, the unknown force accelerating cosmic expansion. Cold dark matter referred to invisible matter moving slowly enough for gravity to shape large structures around it. We cannot see dark matter directly, but its gravitational influence acts like hidden scaffolding beneath the visible universe. Within this model, galaxy formation followed a careful sequence. Dark matter collapsed first into massive halos. Gas then cooled inside those gravitational wells over hundreds of millions of years. Stars ignited. The earliest stellar generations lived briefly and died violently, forging heavier elements through nuclear fusion before scattering them back into space. New stars formed from enriched material. Galaxies slowly accumulated mass across immense stretches of time. Nothing in the process was instantaneous. To build a galaxy comparable to the Milky Way required roughly 1 to 2 billion years under the fastest physically realistic conditions. Every simulation, every observation, every equation pointed toward the same timeline. And for decades, Lambda-CDM survived every challenge placed before it. It correctly predicted the large-scale cosmic web, the distribution of galaxies, fluctuations in the CMB, and the measured age of the universe itself. That success mattered deeply. Scientists trusted the model because it had earned that trust repeatedly through observation and mathematics. Entire careers were built refining its details. Massive supercomputers simulated its predictions. Observatories across Earth and orbit confirmed them again and again. But when James Webb finally looked far enough back into cosmic history, the universe no longer behaved the way the model said it should. On a cold morning in French Guiana, a rocket stood motionless beneath heavy clouds. Inside it rested the most complicated scientific instrument humanity had ever attempted to send into space. Not a probe, not a station, a machine built to look backward across nearly the entire history of the universe. The James Webb Space Telescope began its journey on December 25, 2021, launched aboard a European Ariane 5 rocket. There would be no second attempt. Once separated from Earth, Webb had to unfold itself perfectly through a sequence of 344 separate mechanisms. Hinges, motors, pulleys, cables, tension systems. Any single failure could leave the telescope permanently unusable. Nothing like it had ever been deployed before. The telescope itself was enormous. Hubble's mirror measured 2.4 meters across. Webb's primary mirror stretched 6.5 meters wide, formed from 18 gold-coated hexagonal segments made of lightweight beryllium. Folded for launch, it resembled a machine compressed into impossible geometry. But once opened in space, the mirror created more than 6 times Hubble's light-collecting area. That increase mattered because Webb was never designed to replace Hubble directly. It was designed to see something Hubble largely could not: infrared light. As the universe expands, ancient light traveling across billions of years becomes stretched into longer wavelengths. The earliest galaxies no longer shine mainly invisible light by the time their photons reach us. Their light has shifted into infrared, beyond human vision. Hubble could glimpse fragments of that distant era. Webb was engineered specifically to observe it clearly. But infrared astronomy comes with a problem: heat. Any warm object produces infrared radiation, including the telescope itself. To prevent contamination, Webb travels around a location called Lagrange Point 2, approximately 1.5 million kilometers from Earth. There, the Sun, Earth, and Moon remain on the same side of the spacecraft, allowing a giant sun shield to block their heat continuously. The shield is immense, roughly the size of a tennis court, made from 5 delicate layers of Kapton film, thinner than human hair. On the cold side, Webb operates near negative 233 degrees Celsius. Sensitive enough, engineers once explained, to detect the heat signature of a bumblebee on the Moon. By July 12, 2022, the telescope released its first full-color science images. What appeared on screens around the world looked almost unreal. Thousands of galaxies crowded into tiny fragments of darkness, their light traveling for over 13 billion years before touching Webb's mirror. Scientists expected confirmation. Lambda-CDM had survived decades of testing. Webb was supposed to sharpen the details, refine measurements, and extend observations deeper into the timeline already predicted by cosmology. The telescope was not built to overthrow the model. It was built to complete it with greater precision. But within months, the data arriving from Webb began producing measurements that no simulation expected. Galaxies appeared brighter, larger, and more mature than the timeline allowed. Structures emerged too early, stellar masses climbed too high, and the farther Webb looked into the infant universe, the more uncomfortable the numbers became. The first warning arrived buried inside a survey with a technical name few people outside astronomy had ever heard before. CERS, short for Cosmic Evolution Early Release Science, was designed as one of Webb's first systematic deep field programs. Astronomers pointed the telescope toward a region already studied extensively by Hubble, allowing direct comparison between the old universe we thought we understood and the sharper one Webb could suddenly reveal. At first, the process looked routine. Researchers cataloged faint infrared smudges, measured brightness levels, and estimated distances using redshift. Redshift describes how much light has been stretched by cosmic expansion during its journey across space. A redshift value of 10 means the universe expanded by a factor of 11 after the light was emitted. The higher the redshift, the further backward we are looking through time. Then the numbers stopped making sense. Within months, CERs identified several galaxy candidates with redshifts greater than 10, meaning we were seeing them less than 500 million years after the Big Bang. That alone was remarkable. But the deeper problem appeared when astronomers estimated their mass. These galaxies looked far too large. A team led by astronomer Ivo Labai analyzed 6 of the strongest candidates. Their calculations suggested stellar masses comparable to the modern Milky Way, assembled during an era when the universe should barely have begun forming substantial galaxies at all. Combined together, the estimated mass of those 6 objects exceeded what Lambda-CDM predicted should exist across the observable universe at that moment in cosmic history. Not in one region, everywhere. The findings appeared in February 2023 in the journal Nature. The language inside the paper was unusually direct for academic astronomy. The galaxies were described as inconsistent with current models of galaxy formation. Quietly, carefully, the standard timeline was beginning to fracture. But astronomers remained cautious. Early redshift estimates often rely on photometry, a method using color patterns to estimate distance. Photometric measurements are useful, but imperfect. Dust, brightness, and unusual stellar populations can sometimes imitate extreme distances. The community needed spectroscopy. Spectroscopy measures exact wavelengths of light emitted by an object, producing a far more precise cosmic fingerprint. And when Webb's spectroscopic instruments confirmed several of these distances, the anomaly deepened rather than disappeared. One galaxy became especially difficult to ignore. Jade's GS140, later spectroscopically confirmed at a redshift of 14.32, existed only 290 million years after the Big Bang. Yet it already appeared bright, chemically evolved, and unexpectedly large. Under conventional timelines, there simply had not been enough time for that much structure to emerge. Independent teams reanalyzed the Webb data repeatedly. Different software pipelines were used, different assumptions were tested, alternative explanations were explored, but the central pattern remained stable across studies. The galaxies were real, their distances were real, their masses remained deeply uncomfortable. This was no longer a calibration issue or a single flawed paper. Multiple groups examining separate datasets kept arriving at variations of the same conclusion. The early universe looked older than it was supposed to look. And for the first time in decades, the equations behind modern cosmology were no longer matching the sky above us. Imagine trying to grow an ancient forest in a single night, not by planting mature trees directly into the ground, but by waiting for seeds to form, roots to spread, soil to develop, weather cycles to stabilize, and generations of growth to slowly build, layer upon layer, across centuries. Galaxy formation works in much the same way. It is not one event, it is a chain of physical processes, each dependent on the one before it, and every link consumes time. The early universe began as an almost uniform sea of matter and radiation. Tiny fluctuations in density existed, slight variations left behind from the first moments after cosmic expansion began. Over immense stretches of time, gravity amplified those fluctuations. Regions with slightly more matter pulled in surrounding material, gradually forming dense structures called dark matter halos. Dark matter itself remains invisible, but its gravity shapes the skeleton of the cosmos. Without those halos, galaxies cannot assemble. But even under favorable conditions, gravitational collapse takes tens to hundreds of millions of years. Then comes ordinary matter. Hydrogen and helium gas falls into the dark matter halos, heating violently as it compresses. Before stars can form, the gas must cool by radiating energy away into space. Cooling sounds passive, but in astrophysics it becomes a bottleneck. Hot gas resists collapse. Radiation carries energy outward only gradually across enormous regions, and cooling alone is not enough. The gas must become dense enough for gravity to overwhelm competing forces. Turbulence stirs it apart. Magnetic fields resist compression. Fragmentation breaks clouds into unstable structures. Only when pressure finally gives way can nuclear fusion ignite within collapsing cores. The first stars, known as population 3 stars, were unlike most stars we see today. They formed from pristine hydrogen and helium containing almost no heavier elements. Many were probably enormous, burning through their fuel rapidly before exploding as supernovae. Those explosions seeded surrounding space with carbon, oxygen, iron, and other elements required for later generations of stars. Only after that enrichment process could larger, chemically mature galaxies begin to emerge. Every stage builds upon the previous one. None can be skipped. Under the fastest physically plausible scenarios inside Lambda-CDM, assembling a galaxy with mass comparable to the Milky Way requires roughly 1 to 2 billion years. That estimate already assumes efficient collapse rates, aggressive star formation, and highly favorable conditions. But Webb's galaxies existed after only 290 to 500 million years, not near the lower boundary, far beneath it. The discrepancy is so extreme because the universe was still supposed to be in its early construction phase during that era. Yet Webb's observed systems appearing chemically evolved, luminous, and unexpectedly massive long before the standard timeline allowed such complexity to exist. Astrophysicist Joel Ley, a co-author of one of the major analysis papers, summarized the situation carefully. Scientists, he explained, may need to rewrite galaxy formation itself, or possibly rethink cosmology more broadly. That second possibility carries unusual weight. Changing galaxy formation models adjusts details inside the framework. Rethinking cosmology means questioning the framework itself, the assumptions describing how the universe expanded, evolved, and generated structure after its beginning. And once that door opens, far stranger possibilities begin entering the conversation beside it. Scientists rarely abandon a successful theory immediately. When observations begin drifting away from predictions, the first instinct is usually restraint. Adjust the smaller pieces first, refine assumptions, search for overlooked mechanisms hidden inside the machinery already in place. That is exactly what cosmologists did after Webb's early galaxy measurements arrived. The standard model assumes that only a modest fraction of gas inside a dark matter halo becomes stars. Roughly 10 to 20% of the available material collapses successfully. The rest is pushed outward again through violent stellar processes. Young stars emit intense ultraviolet radiation. Supernova explosions generate expanding shock waves. Together, these effects heat surrounding gas and eject it back into interstellar space. This process is called stellar feedback. Feedback acts like a regulator. As star formation increases, radiation pressure rises with it, limiting how efficiently additional stars can form. Without that braking mechanism, galaxies and simulations become unrealistically massive far too quickly. For decades, feedback physics helped Lambda-CDM match the observed universe remarkably well. But Webb's galaxies forced researchers to ask an uncomfortable question. What if the early universe formed stars much more efficiently than modern galaxies do? In principle, higher efficiency could shorten the timeline dramatically. If gas converted into stars faster than expected, perhaps those ancient galaxies simply assembled earlier than our models predicted. The idea remained conservative because it preserved the broader cosmological framework while adjusting only the details of galaxy formation itself. Several proposals emerged quickly. One influential study in 2023, led by astrophysicist Avishai Deckel, explored the possibility of cold streams. These streams are dense filaments of relatively cool gas flowing directly into young galaxies along the structure of the cosmic web. Instead of waiting for hot gas clouds to cool slowly over time, cold streams could feed galaxies continuously with fresh material already capable of collapsing into stars. The process resembled opening hidden supply lines deep inside the early universe. Another hypothesis focused on the first stellar populations themselves. Modern galaxies produce stars across a broad range of masses, but the earliest stars may have followed a different distribution called a top-heavy initial mass function. In simple terms, the infant universe might have produced disproportionately massive stars, some hundreds of times heavier than the Sunday. Massive stars burn hotter and faster. A star like our Sun survives for billions of years. Extremely massive stars can exhaust their fuel in only a few million years before exploding as supernovae. That rapid cycle accelerates chemical enrichment and generates heavier elements much sooner, potentially speeding up galaxy growth. For a time, these modifications appeared promising. Simulations incorporating cold streams and top-heavy star formation successfully reproduced some of Webb's less extreme observations. Certain galaxies no longer looked impossible. The tension softened at the edges. But not everywhere. Jade's GS Z14-0 remained deeply problematic. Observed only 290 million years after the Big Bang, it still appeared too luminous, too mature, and too massive for even the revised models to comfortably explain. Each adjustment improved isolated cases while leaving the most extreme outliers standing stubbornly beyond the boundary. At that point, the problem changed shape. The issue was no longer whether one mechanism inside galaxy formation needed refinement. The issue became whether the underlying cosmological framework itself had encoded the wrong conditions from the very beginning. Long before Webb detected galaxies arriving too early, another discrepancy had already begun quietly unsettling cosmology. It did not emerge from dramatic images or impossible structures. It appeared inside measurements, buried within decimal places that refused to align. The problem centered on the expansion rate of the universe. Astronomers describe that rate using the Hubble constant, named after Edwin Hubble. It measures how quickly galaxies move apart as space expands, expressed in kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light years. The larger the Hubble constant, the faster the universe grows. For years, scientists expected increasingly precise observations to converge toward a single answer. Instead, the opposite happened. One method estimates the Hubble constant by studying the early universe. Researchers analyzed tiny fluctuations preserved in the cosmic microwave background, the ancient radiation released after the primordial plasma cooled enough for light to travel freely. Those fluctuations behave like frozen sound waves from the infant cosmos. Using the Lambda-CDM framework, cosmologists can evolve that early state forward mathematically and predict the modern expansion rate. That approach produces a value near 67.4 kilometers per second per megaparsec. A second method measures the nearby universe directly. Astronomers use Cepheid variable stars, pulsating stars whose brightness changes predictably over time as cosmic distance markers. By calibrating those distances carefully and extending them outward using type Ia supernovae, which explode with nearly uniform brightness, researchers can calculate expansion from observed galaxies themselves. That method consistently gives a higher value, near 73 kilometers per second per megaparsec. The gap appears small at first glance, roughly 8%, but modern cosmology operates with extraordinary precision. The disagreement reached what physicists call 5 sigma significance, meaning the probability that random statistical noise caused the discrepancy is less than 1 in 3.5 million. The universe was producing two incompatible answers to the same question. At first, many scientists suspected hidden observational errors. Perhaps dust affected brightness measurements. Perhaps calibration methods drifted subtly over time. Instrument effects, data processing biases, unknown systematic uncertainties. Entire teams spent years searching for mistakes large enough to close the gap. The discrepancy survived every attempt. Astrophysicist Adam Rees, who shared the Nobel Prize for discovering dark energy, eventually stated openly that the Hubble tension was likely signaling new physics. Not bad measurements, something deeper. Part of Webb's mission involved testing that possibility directly. Because Webb observes infrared light with far greater clarity than Hubble, it could measure Cepheid variable stars through dust clouds more accurately than any previous telescope. If hidden observational problems existed inside the local measurements, Webb might finally expose them. But the new observations did not reduce the tension. They strengthened it. Webb's infrared Cepheid measurements confirmed the higher local expansion rate with even greater confidence. The contradiction between the early universe calculations and the nearby universe observations remained intact. In some analyses, it became harder to dismiss than before. And now the situation looked different than it had only a few years earlier. The impossible galaxies challenged the universe's timeline for structure formation. The Hubble tension challenged the expansion history encoded inside the same cosmological model. Two separate observational problems, discovered through entirely different methods, were both pointing toward incompleteness inside Lambda-CDM. Not collapse, not failure, but cracks spreading through foundations once considered almost untouchable. Empty space was once expected to be quiet. For much of the 20th century, cosmologists assumed gravity would gradually slow the universe's expansion over time. Galaxies moved apart after the Big Bang, but their mutual gravity should have acted like a brake, steadily reducing the expansion rate across billions of years. Then, in 1998, two separate research teams studying distant supernovae found something deeply unexpected. The supernovae appeared too faint. Type Ia supernovae are valuable because they explode with nearly uniform brightness, allowing astronomers to estimate cosmic distances with remarkable precision. By comparing how bright those explosions should appear against how bright they actually looked, researchers could determine how far away their host galaxies were. And those galaxies were farther than expected. The expansion of the universe was not slowing down. It was accelerating. The discovery came from teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees. In 2011, the finding earned the Nobel Prize in Physics. But the prize did not solve the mystery. It only confirmed its existence. Something invisible was pushing space apart faster over time. Cosmologists called that unknown influence dark energy. The name sounds concrete, but it is really a placeholder. Dark energy is not a particle we have isolated, or a substance we understand directly. It is the label attached to whatever drives cosmic acceleration. Inside Lambda-CDM, dark energy is treated as a cosmological constant, often represented by the Greek letter lambda. In this interpretation, empty space itself contains a fixed energy density, identical everywhere and unchanging across time. Even the vacuum carries energy. But that explanation creates one of the worst theoretical mismatches in modern physics. Quantum field theory predicts vacuum energy naturally. According to the equations governing quantum fluctuations, empty space should contain an enormous amount of energy. Yet when physicists calculate the expected value, the result exceeds the observed strength of dark energy by roughly 1 part in 10 to the power of 120. It is the largest known discrepancy between theory and observation anywhere in science. For years, researchers tolerated the contradiction because the cosmological constant still matched observational data reasonably well. But new measurements have started disturbing that balance too. In 2024, the Dark Energy Spectroscopic Instrument, known as DESI, released its first major dataset. Mounted on the Mayall telescope in Arizona, DESI mapped more than 6 million galaxies and quasars across vast stretches of cosmic history. By studying baryon acoustic oscillations, ancient pressure patterns frozen into galaxy distributions, scientists reconstructed how expansion changed over time. The early results hinted at something unexpected. Dark energy may not be constant after all. The data suggested its strength could have evolved throughout cosmic history, potentially stronger in the distant past than it is today. If true, the implications become enormous. Stronger early dark energy would alter how quickly matter gathered into galaxies and large structures, potentially helping explain why Webb observed massive systems forming so rapidly after the Big Bang. But a changing dark energy does more than adjust timelines. It removes one of the foundational assumptions inside Lambda-CDM entirely. Once dark energy becomes dynamic rather than constant, The behavior of the early universe no longer follows the simple cosmological picture physicists relied upon for decades. There is a moment in cosmology so early that ordinary language begins to fail around it. A fraction of a second after the universe began, before stars, before atoms, before light moved freely through space, something extraordinary may have happened to reality itself. Space expanded at impossible speed. This idea is called cosmic inflation, and despite its strange implications, it became one of the most successful theories in modern physics. Not because scientists wanted the universe to behave this way, but because several major problems inside the original Big Bang model seemed to disappear once inflation was introduced. One problem involved geometry. Measurements show the universe is astonishingly flat on large scales, meaning parallel light rays travel through space without gradually converging or diverging. But in the standard Big Bang picture alone, even tiny deviations from flatness in the early universe should have grown dramatically over time. The observed balance appeared unnaturally precise. Another issue concerned temperature. The cosmic microwave background looks nearly uniform across opposite sides of the sky. Regions separated by billions of light years possess almost identical temperatures. Yet according to ordinary expansion alone, those regions should never have been close enough to exchange information or energy before the CMB formed. This became known as the horizon problem. Then there were magnetic monopoles. Particle physics predicts isolated magnetic charges should have formed abundantly during the universe's earliest moments. But despite decades of searching, none have ever been observed. In 1980, physicist Alan Guth proposed a radical solution connecting all three mysteries at once. During an unimaginably brief interval, between roughly 10 to the negative 36 and 10 to the negative 32 seconds after the beginning, the universe underwent exponential expansion. Space doubled in size repeatedly at staggering speed, expanding by at least a factor of 10 to the 26th power. Inflation flattened the universe by stretching any original curvature beyond detectability. It solved the horizon problem because distant regions had once been close enough to equalize conditions before expansion separated them. And it diluted magnetic monopoles so thoroughly that finding one became extraordinarily unlikely. The theory fit remarkably well. Over time, inflation became woven directly into Lambda-CDM itself. Cosmologists treated it not as speculation, but as a foundational component of the modern universe. Tiny quantum fluctuations generated during inflation even appeared capable of explaining the initial density variations that later became galaxies and clusters. But inflation carried a consequence few expected initially. Stopping inflation everywhere at the same moment turns out to be extremely difficult. In 1983, physicist André Linde showed that quantum fluctuations inside the inflationary field could keep expansion continuing indefinitely through most of space. Inflation would end randomly only in isolated regions, while the surrounding space kept inflating faster than light could cross it. Each region where inflation stopped became its own expanding cosmos. Separate patches would evolve independently, disconnected forever from one another by the relentless expansion between them. Different regions could emerge with different densities, different physical conditions, perhaps even different constants governing matter and energy. And that is where the multiverse enters physics. Not as philosophy, not as science fiction, but as an unexpected mathematical consequence emerging naturally from one of cosmology's most successful theories about the universe's first moments. Picture the observable universe for a moment. Every galaxy ever photographed, every star that has ever illuminated a planet, every black hole, nebula, and drifting cloud of gas, all contained inside a region roughly 93 billion light-years across, vast beyond intuition, yet within eternal inflation, that entire volume may represent only a single pocket of reality, one bubble among countless others. In this framework, inflation does not end everywhere simultaneously. Most of space continues expanding exponentially forever, stretching faster than light itself can travel. But in isolated regions, inflation slows and releases its energy into ordinary matter and radiation. Those regions become bubble universes, self-contained cosmic domains emerging from the surrounding inflating space. Our universe would be one such bubble. Inside each bubble, expansion proceeds more gently, allowing particles, atoms, stars, and galaxies to form. Observers within those regions experience what appears to be a complete cosmos with its own beginning and physical laws. To us, the Big Bang marks the birth of everything we can observe. But within eternal inflation, it may simply mark the local ending of inflation inside our particular bubble. Beyond it, inflation continues endlessly. That creates a strange consequence. No matter how advanced a civilization becomes, no signal can travel from one bubble universe to another. The inflating space between them expands too rapidly. Even light cannot bridge the distance. The separation is not technological. It is built directly into the geometry of space-time itself. Causally disconnected. Each bubble may also inherit different physical conditions depending on how inflation ended locally. Tiny variations in the inflationary field could alter the properties of matter, energy, and space-time from one bubble to the next. The speed of light, the strength of gravity, the mass of fundamental particles, even the value of dark energy could differ across separate universes. Our bubble appears unusually hospitable. Hydrogen remains stable long enough for stars to burn across billions of years. Carbon forms efficiently inside stellar cores through delicate nuclear resonances. Chemistry becomes complex. Planets emerge. Biology evolves. Conscious observers eventually appear capable of asking why the universe allows any of this at all. But many bubbles might not permit such complexity. If gravity were significantly stronger, stars could collapse and burn out rapidly, leaving little time for planetary systems to stabilize. If electromagnetism behaved differently, electrons might never bind into atoms. Some universes could expand too violently for galaxies to form. Others might collapse almost immediately after their birth. Reality itself becomes variable. What makes this unsettling for many physicists is that the multiverse was not originally invented to explain fine-tuning or philosophical questions about existence. It emerged accidentally from inflationary mathematics. The same equations developed to solve problems inside the early universe kept generating additional universes whether researchers wanted them or not. And the equations themselves work remarkably well inside our own cosmos. Inflation correctly predicts patterns observed in the cosmic microwave background. It explains large-scale structure formation and the near flatness of space-time. Once those equations are accepted, eternal inflation follows naturally in many versions of the theory. The multiverse arrived less like a deliberate hypothesis and more like an unavoidable side effect. A passenger hidden inside the mathematics from the very beginning, waiting for physicists to notice it was there. A map of the early universe, is never only a map of galaxies. Hidden underneath every ancient structure lies a record of the conditions that produced it long before the first stars ignited. When Webb detected galaxies assembling too quickly, cosmologists did not just see a problem with galaxy formation. They saw a possible problem with the universe's opening conditions themselves. And those conditions come from inflation. Inside Lambda-CDM, inflation is usually modeled in a relatively simple way. A single scalar field, meaning a field with only magnitude and no direction, slowly rolls down an energy landscape before inflation ends smoothly and uniformly across space. This approach is called single-field slow-roll inflation. For decades, it matched observations well enough to become embedded deeply into modern cosmology. But Webb's galaxies are beginning to strain that simplicity. If massive structures formed earlier than expected, then something about the infant universe may have differed from the assumptions encoded inside the standard inflationary picture. Perhaps density fluctuations were initially stronger in certain regions. Perhaps matter collapsed more efficiently because expansion behaved differently at early times. Perhaps dark energy evolved in ways the simple model does not allow. None of those possibilities automatically destroys inflation. Instead, they imply inflation may have been more complicated than originally assumed. That distinction matters because more complicated inflation is exactly what eternal inflation theories already predict. In many versions of the theory, inflation does not unfold with perfect smoothness. Quantum fluctuations continuously disturb the inflationary field, causing different regions of space to evolve differently as expansion proceeds. The early universe becomes uneven at a fundamental level. Physicist André Linde explored versions of this idea through chaotic inflation models during the 1980s. In those frameworks, inflation can end at different moments and under different conditions across separate regions of spacetime. Some domains continue inflating, while others settle into ordinary cosmic evolution. Even inside our observable universe, subtle variations could survive from that chaotic process. If the distant region Webb is observing happened to emerge from slightly enhanced density fluctuations, galaxy formation there could accelerate dramatically. Matter would collapse sooner. Dark matter halos would grow faster. Stars would ignite earlier than the standard average timeline predicts. The key point is often misunderstood. This does not require Webb to literally observe another universe. No collision between bubbles is necessary. The connection runs deeper and more technical than that. The impossible galaxies force cosmologists to reconsider the inflationary assumptions built directly into Lambda-CDM. And once those assumptions become more flexible, eternal inflation naturally becomes harder to avoid mathematically. The logic forms a chain. Webb detects structures too mature for standard cosmology. Explaining those structures may require altered inflationary conditions. Altered inflationary conditions align naturally with more chaotic and uneven inflation models. Those models frequently produce eternal inflation and bubble universes as direct consequences. Step by step, the framework shifts. That is why the discussion surrounding Webb reaches beyond ordinary galaxy evolution. The telescope did not discover proof of the multiverse. No serious cosmologist claims that. But the observations are pushing theorists toward versions of inflation already associated with multiverse physics. And notably, the direction of those revisions keeps pointing the same way, toward a universe whose beginning was less orderly, less uniform, and potentially far larger than the observable cosmos alone suggests. Far beneath the scale of galaxies, deeper even than atoms, physics encounters another fracture, not observational this time, but mathematical. Two foundational theories describe reality with extraordinary accuracy, yet refuse to fit together cleanly. Quantum mechanics governs the microscopic world. General relativity governs gravity, space-time, and the large-scale universe. Separately, both theories work astonishingly well. Together, their equations break apart under extreme conditions such as black holes and the earliest moments after the Big Bang. For decades, physicists searched for a framework capable of unifying them. One of the most ambitious attempts became string theory. Instead of treating fundamental particles as dimensionless points, string theory proposes that the smallest constituents of nature are tiny one-dimensional strings vibrating at different frequencies. An electron would correspond to one vibrational pattern, a quark to another. In principle, every particle and force could emerge from variations of the same underlying object. Reality becomes music at microscopic scale. The mathematics required to make string theory internally consistent quickly grew strange. The equations worked only if space-time contained additional dimensions beyond the familiar 3 dimensions of space and 1 of time. Depending on the version, the universe required 10 or 11 total dimensions. But we do not experience those extra dimensions directly. To explain that, theorists proposed compactification. The additional dimensions are curled into incredibly tiny geometric shapes, folded so tightly that no existing particle accelerator can probe them directly. Different ways of curling those dimensions produce different physical laws inside the resulting universe. And there are many possible ways to fold them. The number of mathematically stable configurations is often estimated around 10 to the power of 500. This enormous collection became known as the string landscape. Each vacuum state, meaning each distinct compactification pattern, generates different constants governing matter and energy, a different electron mass, a different gravitational strength, different chemistry entirely. Initially, many physicists found the landscape disturbing. Fundamental physics traditionally seeks uniqueness, one elegant equation describing one inevitable universe. The landscape suggested something else entirely, not one possible reality, but an almost unimaginable variety of them. But over time, some researchers began interpreting that multiplicity differently. In 2003, physicist Leonard Susskind argued that the string landscape combined naturally with eternal inflation. Inflation could continuously generate new bubble universes, while the landscape supplied a vast menu of possible physical laws for those universes to inherit. The Anthropic principle entered the discussion quietly after that. Most universes in the landscape would likely remain sterile. Some might collapse instantly. Others might never form atoms or stable stars. We find ourselves inside a universe compatible with chemistry and observers, simply because only such universes can produce beings capable of asking the question. Not design, selection. Part of the motivation for the Large Hadron Collider at CERN involved searching for supersymmetry, a proposed extension of particle physics closely connected to many versions of string theory. Yet after more than 15 years of operation, no supersymmetric particles have been confirmed experimentally. That absence constrains many string models significantly, but it does not eliminate the landscape itself. If anything, attention has shifted increasingly toward the multiverse implications emerging from the theory rather than the simpler particle predictions once expected at accelerator energies. And that convergence remains striking. Inflationary cosmology and string theory began from entirely separate problems. One attempted to explain the early universe, the other attempted to unify the laws of physics. Yet both frameworks, independently, and without coordination, kept arriving at the same unsettling possibility. Reality may contain far more universes than the one we inhabit. The deeper physicists examine reality, the narrower the margins begin to look. Not approximately balanced, precisely balanced. The universe appears calibrated within astonishingly small tolerances, as though the laws governing matter and energy sit delicately inside a range where complexity barely becomes possible at all. This is known as the fine-tuning problem. One of the most striking examples involves dark energy. The cosmological constant determines how strongly empty space drives cosmic expansion. If that value were even slightly larger, matter would have dispersed too quickly for galaxies or stars to form. Slightly smaller, and gravity could have reversed expansion early, collapsing the universe before structure emerged. The required precision is staggering. The observed value must fall within roughly 1 part in 10, raised to the power of 120. Quantum theory predicts vacuum energy enormously larger than what astronomers actually measure. The mismatch has become so severe that physicists sometimes call it the worst prediction in physics. And the tuning does not stop there. The strong nuclear force binds protons and neutrons together inside atomic nuclei, increase its strength by only about 2%, and nearly all hydrogen formed after the Big Bang would have fused rapidly into helium. Without hydrogen, long-lived stars like the Sun could not exist. Water chemistry disappears. Organic molecules become extraordinarily unlikely. A slightly weaker strong force creates different catastrophes. The electromagnetic force carries similar sensitivity. Reduce it modestly, and electrons no longer remain bound reliably to atomic nuclei. Stable atoms dissolve. Chemistry itself breaks apart before molecules can ever form. Even the existence of matter required extraordinary imbalance during the universe's earliest moments. The Big Bang should have produced matter and antimatter in equal amounts. If that had happened exactly, every particle would eventually have annihilated with its opposite, leaving behind only radiation. But for roughly every billion antimatter particles, the early universe contained 1,000,000,001 matter particles. That tiny excess became everything physical we know. Every galaxy Webb observes, every planet, every living organism, every atom inside your body traces back to that minute asymmetry. Then there is carbon. In 1953, astrophysicist Fred Hoyle realized that carbon production inside stars required an extremely specific nuclear resonance, a precise energy state within the carbon-12 nucleus. Without it, stars would produce almost no carbon at all. Hoyle predicted the resonance mathematically before it had been observed experimentally, reasoning backward from the simple fact that carbon-based life exists. Later experiments confirmed the resonance exactly where his calculations required it to be. These are not vague philosophical observations. They are quantitative measurements with published sensitivity ranges. Tiny shifts in physical constants produce universes radically different from ours, often sterile and structureless. That leaves physics facing 3 broad possibilities. First, the constants may simply be extraordinary coincidences, values selected randomly against overwhelming odds. Second, some deeper undiscovered law may force the constants to possess exactly these values and no others. Or third, an enormous number of universes may exist with varying physical laws, making at least some life, permitting universes statistically inevitable. This is why the multiverse persists scientifically. Not because physicists necessarily prefer it emotionally, but because fine-tuning increasingly resembles a measurable problem requiring explanation. Once reality appears balanced on such narrow margins, the existence of many universes with many combinations of laws becomes one of the few frameworks capable of absorbing that improbability naturally. Across the entire sky, the cosmic microwave background appears astonishingly smooth. Tiny temperature variations exist, but most differ by only millionths of a degree. The early universe, despite all the galaxies and clusters that would later emerge from it, was remarkably uniform, which is why one region continues to trouble cosmologists. In 2004, researchers studying data from the Wilkinson Microwave Anisotropy Probe, usually called WMAP, identified an unusually cold area within the microwave background. The anomaly appeared in the direction of the constellation Eridanus, spanning an immense circular region across the sky. It became known simply as the cold spot. The temperature difference measured roughly 70 microkelvin colder than the surrounding cosmic microwave background. That sounds negligible. But within the statistical structure of the early universe, the scale of the anomaly mattered far more than the temperature itself. It was too large. The cold spot spans roughly 1 billion light-years in apparent diameter, making it difficult to explain through ordinary fluctuations alone. Standard cosmological models predict occasional irregularities, but structures of this size become increasingly improbable. At first, astronomers searched for a conventional explanation. One leading possibility involved a supervoid, an enormous underdense region containing fewer galaxies than average. If microwave photons traveled through such a void while the universe expanded, they could lose energy through a process called the integrated Sachs-Wolf effect, slightly cooling the observed radiation by the time it reached Earth. In 2015, surveys confirmed a vast supervoid in the same direction. The structure stretched approximately 1.8 billion light-years across and appeared around 20% less dense than surrounding cosmic regions. For a moment, the puzzle seemed close to resolution. But detailed calculations complicated the picture again. The void could account for part of the temperature drop, but not all of it. The cold spot remained colder than the supervoid alone should produce under standard cosmological assumptions. Something still appeared missing from the explanation. That gap reopened stranger possibilities. In 2017, physicist Laura Mersini-Houghton and collaborators proposed that the cold spot might represent evidence of interaction between our universe and another inflationary bubble. In eternal inflation models, neighboring bubble universes could occasionally influence one another gravitationally during the earliest phases of cosmic expansion, not through travel or communication, only through distortions imprinted onto space-time itself. According to the proposal, the mass energy associated with a neighboring bubble universe could have altered the path of microwave photons near the boundary between cosmic regions, leaving behind a circular temperature anomaly embedded inside the CMB. Importantly, the idea remains speculative. No observation has confirmed the cold spot as evidence of another universe. Many cosmologists still favor the statistical fluctuation explanation, arguing that sufficiently large universes naturally produce rare anomalies occasionally. Given enough cosmic territory, unusual patterns become inevitable somewhere. But the multiverse interpretation has not been ruled out either. That uncertainty matters because the cold spot represents one of the few multiverse-related ideas producing potentially testable observational consequences. The anomaly exists physically inside the data. Satellites have measured it repeatedly. The European Space Agency's Planck mission later mapped the cosmic microwave background with even greater precision, and the cold spot remained visible there as well. A feature without consensus. Perhaps it is simply an unlikely fluctuation inside a universe vast enough to generate statistical oddities naturally. But there remains another possibility lingering quietly beneath the data: that the oldest light in the cosmos may carry the imprint of something beyond our own cosmic horizon. A single electron passing through two slits can behave like a wave moving through both openings simultaneously. Yet, when measured, it appears at only one location. Quantum mechanics predicts this behavior with extraordinary accuracy, but underneath those predictions sits a question physicists still debate a century later. What exactly happens during measurement? Before observation, quantum systems exist in what is called superposition, a combination of multiple possible states at once. A particle can possess different positions, energies, or directions simultaneously, according to the mathematics describing it. These possibilities are encoded inside something called the wave function, a mathematical object containing all potential outcomes. Then observation seems to change everything. Under the traditional Copenhagen interpretation, developed largely through the work of Niels Bohr during the 1920s, the wave function collapses when a measurement occurs. One outcome becomes real. The alternatives disappear completely. The equations predict probabilities. Observation selects reality. For decades, many physicists accepted this framework pragmatically because it worked operationally. Quantum mechanics remained the most experimentally successful theory ever created. But some researchers found the idea of wave function collapse deeply unsatisfying. The equations themselves never specify exactly when collapse happens or what physically causes it. Then, in 1957, a graduate student at Princeton proposed something radical. Hugh Everett III suggested that collapse never occurs at all. According to Everett's interpretation, every possible outcome permitted by quantum mechanics actually happens. When a quantum event takes place, the universe branches into separate versions corresponding to each possible result. One branch contains one outcome, another branch contains another. Observers inside each branch experience only their own version of events and remain unaware of the others. This became known as the many worlds interpretation. Inside this framework, the wave function evolves smoothly and continuously forever without collapse. Reality itself constantly branches through quantum interactions. Every radioactive decay, every photon absorption, every molecular collision, every neural process inside living brains, the branching never stops. The number of resulting worlds becomes effectively infinite. Unlike the inflationary multiverse, which emerges from cosmological expansion, the quantum multiverse operates through probability and measurement. These universes do not sit separated across distant regions of space-time. They occupy overlapping quantum histories, branching from shared origins, different mechanism, different structure. Importantly, many worlds is not considered fringe by many working physicists. Researchers such as David Deutsch and Sean Carroll openly defend it. Carroll, in particular, argues that many worlds represents the most literal reading of quantum mechanics because it accepts the equations exactly as written without adding extra collapse rules unsupported by the mathematics itself. In that sense, the interpretation removes assumptions rather than adding them. Whether many worlds is ultimately correct remains unresolved. Competing interpretations of quantum mechanics still exist, and no experiment has definitively distinguished among them. But the broader pattern inside modern physics has become difficult to ignore. Inflation points toward multiple universes through cosmology. String theory approaches similar conclusions through extra dimensions and fundamental particles. Quantum mechanics arrives independently through the mathematics of probability itself. Three separate roads, three different starting points, and without coordination among them, all three continue drifting toward variations of the same unsettling possibility that reality may be far larger and stranger than a single universe alone. There is a line in science that cosmology keeps approaching carefully, sometimes uneasily, a point where observation fades, equations continue, and physicists must decide what still counts as legitimate knowledge when direct measurement becomes impossible. The multiverse sits directly on that boundary. The central criticism is straightforward. If other universes remain permanently causally disconnected from ours, meaning no signal or particle can ever travel between them, then no experiment can directly observe them. Without direct observational access, critics argue the multiverse becomes unfalsifiable and therefore falls outside science itself. Physicist Lee Smolin has argued this point forcefully for years. Drawing from philosopher Karl Popper's principle of falsifiability, Smolin maintains that scientific theories must make predictions capable of being proven wrong experimentally. If no observation could ever contradict the multiverse, then according to that standard, the idea risks becoming metaphysics rather than physics. Many scientists take this objection seriously. But the discussion becomes more complicated once indirect evidence enters the picture. Modern physics already contains entities inferred long before direct detection. Black holes existed mathematically decades before observational confirmation. Neutrinos were proposed to preserve energy conservation before experiments found them. Dark matter and dark energy themselves remain undetected directly even now. Inference matters in science. The question becomes whether a theory produces observable consequences inside our own universe, and some multiverse-related models potentially do exactly that. Cosmologists have searched cosmic microwave background data for circular temperature signatures consistent with collisions between inflationary bubble universes. The Planck satellite examined these possibilities with extraordinary precision. The results remained inconclusive. No confirmed collision signatures appeared, but importantly, the searches did not eliminate the possibility either. Certain classes of bubble interactions remain mathematically consistent with existing observations. Other indirect routes continue emerging. If the Hubble tension eventually requires modifications to inflation matching eternal inflation scenarios, that would strengthen the broader framework predicting multiple universes. Similarly, if Webb's impossible galaxies survive continued scrutiny and demand non-standard inflationary conditions, the models explaining them may naturally point toward eternal inflation as a consequence. Evidence accumulates structurally. Some theorists also emphasize statistical prediction. Eternal inflation and landscape models imply probability distributions for physical constants across universes. If our measured constants fall naturally inside those predicted distributions, rather than appearing arbitrarily exceptional, that becomes supporting evidence, though never definitive proof. Physicist Max Tegmark argues that the multiverse is not uniquely speculative by scientific standards. Dark matter, dark energy, and inflation itself were all accepted primarily because they explained observed phenomena coherently before direct confirmation existed. The multiverse, in this view, belongs to the same inferential tradition, but disagreement remains healthy. At the frontier of cosmology, the argument is no longer only about universes. It becomes a debate about the structure of science itself. What level of indirect evidence should count? How far can mathematical consistency extend before observation must intervene? Which questions remain scientifically meaningful even if direct measurement appears permanently unreachable? These are not distractions from cosmology. They are part of cosmology now. Because once physics begins exploring realities potentially larger than the observable universe, defining the limits of scientific inquiry becomes inseparable from defining the universe itself. A fish born beneath the ocean never wonders why it finds water everywhere. The environment feels ordinary precisely because any fish born elsewhere would never survive long enough to ask the question at all. The anthropic principle applies similar logic to the universe. In 1973, physicist Brandon Carter formally described the idea while discussing the apparent fine-tuning of physical constants. The principle begins from a simple observation that any universe observed by conscious beings must necessarily contain conditions allowing conscious beings to emerge. Otherwise, no observers exist. This version is usually called the weak anthropic principle. It does not claim the universe was designed intentionally for life. It does not invoke purpose or direction. Instead, it describes a selection effect. We observe a universe compatible with our existence because incompatible universes contain nobody capable of making observations. Applied to a multiverse, the reasoning changes scale dramatically. If an enormous number of universes exist with different physical constants, then most may remain sterile forever. Some expand too rapidly for stars to form. Others collapse quickly. Some never produce stable atoms or long-lived chemistry, but within a sufficiently vast collection, a few universes inevitably possess the narrow conditions required for complexity and observers. We find ourselves inside one of those rare regions simply because we could not exist anywhere else. The logic resembles Earth's habitability. Our planet was not necessarily designed for life. Rather, living organisms can only evolve on worlds already compatible with biology. If Earth had remained molten, airless, or frozen solid permanently, no observers would exist here debating the question. Still, many physicists remain uncomfortable with anthropic reasoning. It can feel circular, almost evasive. Explaining observed conditions by saying observers require those conditions risks sounding less like physics and more like philosophical bookkeeping. Critics argue it weakens the search for deeper physical laws by replacing explanation with statistical inevitability. But then, something unexpected happened. In 1987, physicist Steven Weinberg applied anthropic reasoning mathematically to the cosmological constant long before dark energy had been measured directly. Weinberg reasoned that if the cosmological constant were too large, galaxies would never form because matter would disperse too rapidly through accelerated expansion. Observers would never emerge. Using that logic, he calculated that the cosmological constant should be small enough to permit galaxy formation, but not necessarily equal to zero. At the time, many physicists still hoped the constant would vanish entirely through some unknown symmetry. Then came 1998. Astronomers discovered dark energy through distant supernova observations, confirming that the universe's expansion is accelerating. More surprisingly, the measured value of dark energy fell within the same general anthropic range Weinberg had predicted over a decade earlier. The prediction worked. Not perfectly, not with infinite precision, but well enough to become one of the most discussed successes associated with anthropic reasoning in modern cosmology. A value estimated partly from the requirement that observers exist matched the observed behavior of the universe's dominant energy component. That result does not prove the multiverse exists, but it changed the conversation permanently. The Anthropic principle stopped being dismissed entirely as philosophical speculation because it had produced something physics respects deeply, a successful prediction tied directly to measurable reality. Most of the universe does not shine. No telescope has ever photographed it directly. No detector has conclusively captured one of its particles. Yet galaxies rotate as though it surrounds them, clusters move as though it outweighs everything visible, and the large-scale structure of the cosmos appears sculpted by its gravity. Physicists call it dark matter. Current measurements suggest dark matter comprises roughly 27% of the universe's total energy content. Ordinary matter, everything made from atoms, stars, planets, gas clouds, and living organisms, accounts for only about 5%. The rest remains invisible. The evidence first became impossible to ignore during the 1970s through the work of astronomer Vera Rubin. Rubin studied rotation curves inside spiral galaxies, measuring how quickly stars orbited at different distances from galactic centers. The outer stars moved too fast. According to Newtonian gravity, orbital speeds should decrease farther from the dense central regions where most visible mass resides. Instead, the rotation curves remained unexpectedly flat. Something unseen appeared to provide additional gravitational pull extending far beyond the visible galaxy itself. And the anomaly repeated everywhere. Another line of evidence emerged through gravitational lensing, the bending of light by gravity predicted by Einstein's general relativity. Massive galaxy clusters distort light from more distant galaxies behind them, acting like enormous cosmic lenses. By measuring the degree of distortion, astronomers can estimate total mass inside the cluster. The visible matter never accounts for all of it. Then came the bullet cluster, one of the most important observations in modern cosmology. Roughly 150 million years ago, two massive galaxy clusters collided. Ordinary gas within the clusters interacted violently, heating through friction and becoming visible in X-ray observations. But the dominant gravitational mass behaved differently. Lensing maps showed most of the mass passed through the collision almost unaffected, separating from the slowed gas clouds entirely. Whatever dark matter is, the bullet cluster demonstrated it interacts weakly with normal matter and with itself. Invisible, massive, collisionless. Physicists have proposed several candidates. One major possibility involves WIMPs, short for weakly interacting massive particles. These hypothetical particles emerge naturally in some supersymmetry theories and have been searched for extensively at underground detectors and particle accelerators, including the Large Hadron Collider at CERN. So far, nothing definitive has appeared. Another candidate involves axions, ultralight particles searched for through delicate electromagnetic resonance experiments. Then, there are primordial black holes, compact objects potentially formed during extreme density fluctuations shortly after the Big Bang itself. Primordial black holes connect directly to Webb's anomalies. If large populations of them existed in the infant universe, they could have acted as early gravitational seeds, accelerating matter collapse long before standard galaxy formation models predict. Massive galaxies might then emerge earlier without requiring entirely new cosmological physics. Different dark matter, different timeline. Yet, despite more than 50 years of evidence from galactic rotation, lensing, cluster dynamics, and cosmic structure formation, dark matter remains undetected directly as of 2025. Astronomers observe its gravitational influence constantly while remaining unable to identify its true nature, and that uncertainty reaches deeper than a missing particle. Dark matter forms the invisible scaffolding underlying cosmic structure itself. Galaxies assemble inside its gravitational wells. Clusters follow its distribution, change the properties of dark matter, and the entire chronology of the universe changes with it. High in the mountains of Arizona, beneath dry desert air and unusually dark skies, a telescope now spends its nights measuring the universe one spectrum at a time, not photographing galaxies for beauty, but recording their distances with relentless precision. The instrument is called DESI. The Dark Energy Spectroscopic Instrument sits atop the 4-meter Mayall telescope at Kitt Peak National Observatory. From a distance, the observatory looks quiet and ordinary against the mountain landscape. Inside, however, thousands of robotic fibers move constantly with microscopic accuracy, repositioning themselves toward distant galaxies every few minutes. 5,000 targets at once. Each robotic positioner locks onto a galaxy or quasar and captures its spectrum during roughly 20-minute exposures. A spectrum spreads incoming light into wavelengths, allowing astronomers to measure redshift precisely and determine how far away an object is across cosmic history. DESI operates at enormous scale. Its 5-year mission aims to map 40 million galaxies and quasars, spanning approximately 11 billion years of cosmic time. The resulting survey will become the largest three-dimensional map of the universe ever assembled, revealing how cosmic expansion evolved across different eras. But DESI is not merely counting galaxies. It is searching for a subtle pattern imprinted shortly after the Big Bang itself. In the infant universe, ordinary matter and radiation existed as an extremely hot plasma where pressure waves moved outward through space, somewhat like sound waves through air. These ripples became known as baryon acoustic oscillations, usually shortened to BAOs, frozen echoes from the early universe. As expansion cooled the plasma and atoms formed, the waves stopped moving but left behind a characteristic separation scale inside matter distribution, roughly 500 million light-years. Galaxies today still preserve traces of that ancient spacing statistically across the cosmic web. By measuring how that scale appears at different distances, astronomers can reconstruct how quickly the universe expanded during different epochs. That reconstruction is where DESI began producing surprises. In April 2024, the collaboration released its first major analysis based on roughly 6 million galaxies and quasars. The data traced cosmic expansion remarkably well across billions of years. But the results did not align perfectly with a constant cosmological constant. The mismatch was subtle, yet persistent. Instead of behaving as a fixed energy density filling empty space uniformly forever, dark energy appeared slightly stronger in the distant past and weaker more recently. Some analyses even suggested it may have crossed what cosmologists call the phantom divide, a boundary separating different expansion behaviors inside cosmological equations. If confirmed, the implications become enormous. Lambda, the term representing dark energy inside Lambda-CDM, would no longer remain constant at all. One of the foundational assumptions underlying the standard cosmological model would require revision. The equations governing cosmic expansion since the Big Bang would need to be rewritten accordingly. And DESI is only beginning. The first year of data represents a fraction of the full survey. Observations continue nightly, while additional datasets undergo processing now. Within the next few years, DESI may either reinforce the current model with greater precision or deepen the cracks already appearing across modern cosmology. The map is still expanding, and with every new measurement, the universe continues revealing that its behavior may be less stable, less predictable, and less understood than physics assumed only a decade ago. The equations describing the Big Bang carry us backward almost all the way to the beginning. Temperatures rise, density increases, space contracts toward an extreme state where matter and radiation become inseparable. Then the mathematics fails. At the singularity, general relativity produces infinities, quantities with no physical meaning. Density becomes infinite. Curvature becomes infinite. Time itself loses coherent definition. The equations stop generating predictions entirely. Standard Lambda-CDM says nothing beyond that boundary. But physicists rarely accept silence comfortably. Over the past several decades, multiple theories have attempted to move past the singularity and describe what, if anything, preceded the observable expansion of our universe. One of the most unusual came from physicist Roger Penrose. Penrose proposed conformal cyclic cosmology, often shortened to CCC. In this framework, the universe does not begin once. Instead, cosmic history unfolds through endless cycles called aeons. Each aeon expands gradually toward heat death, a state where stars extinguish, black holes evaporate, and ordinary matter disappears almost completely. Eventually, only massless particles remain. At that stage, Penrose argues the distinction between infinitely large and infinitely small loses meaning mathematically. Without mass, spacetime can be rescaled conformally, allowing the infinitely expanded future of one aeon to connect naturally to the next Big Bang. The universe begins again. Penrose also claimed possible observational evidence. He identified unusual circular temperature patterns inside the cosmic microwave background that he called Hawking points, potential remnants from evaporating supermassive black holes belonging to a previous cosmic cycle. The claim remains deeply controversial. Several independent research groups dispute whether the statistical significance of those temperature rings exceeds ordinary random fluctuations inside the microwave background. Yet the proposal has not disappeared entirely from serious cosmological discussion. Another approach emerges from quantum gravity. Loop quantum cosmology attempts to apply quantum mechanics directly to spacetime itself. Instead of treating space as perfectly continuous, the theory describes it as quantized at extremely small scales, composed of discrete units somewhat analogous to atoms of geometry. Inside this framework, singularities vanish. As the universe contracts toward extreme density, quantum gravitational effects generate repulsive pressure strong enough to halt collapse before infinities form. The result becomes a big bounce rather than a singular beginning. A prior universe contracts, rebounds, and expands again into the cosmos we observe now. Time extends indefinitely in both directions. Then there is the ekpyrotic model, developed partly by physicist Paul Steinhardt. In this picture, our observable universe exists on a four-dimensional membrane, often called a brane, embedded inside higher dimensional space. The Big Bang occurred when two such branes collided, releasing enormous energy and initiating expansion. And the collisions may repeat cyclically. Each theory paints a profoundly different picture of cosmic origins, endless cycles, quantum rebounds, higher dimensional collisions. Yet, all attempt to solve the same fundamental problem left unresolved by standard cosmology. What existed before the beginning? Importantly, these ideas are not purely philosophical. Each produces different predictions involving gravitational waves, cosmic microwave background structure, and large-scale galaxy distribution. Instruments like Webb, Planck, and future gravitational wave observatories may eventually distinguish among them observationally. The universe may still remember what came before the Big Bang. If so, the evidence could already be traveling toward us now through the oldest light and deepest structures in existence. For centuries, astronomy depended entirely on light. Visible light first, then radio waves, infrared radiation, ultraviolet emissions, X-rays, and gamma rays. Every telescope humanity ever built translated some form of electromagnetic radiation into information about the cosmos. Even Webb, despite all its sophistication, still observes light stretched across space and time. But spacetime itself can also vibrate. In 1916, Albert Einstein predicted that accelerating massive objects should generate ripples moving through spacetime at light speed. These ripples became known as gravitational waves. For nearly a century, they remained theoretical because the distortions involved were unimaginably small. Then, in September 2015, humanity detected one. The observatory responsible was LIGO, a pair of enormous interferometers located in Louisiana and Washington state. Each facility uses laser beams traveling through 4-kilometer vacuum tunnels to measure minute distortions in spacetime itself. The detected signal came from 2 black holes merging roughly 1.3 billion light-years away. Each black hole possessed about 30 times the Sun's mass. As they spiraled inward, they radiated gravitational energy outward through the universe. By the time the signal reached Earth, it altered LIGO's detectors by less than 1,000th the diameter of a proton. Yet the signal was unmistakable. In 2017, physicists Kip Thorne, Rainer Weiss, and Barry Barish received the Nobel Prize for the achievement. A completely new way of observing reality had opened. And unlike light, gravitational waves can carry information from eras otherwise inaccessible. The cosmic microwave background formed roughly 380,000 years after the Big Bang, when the universe cooled enough for photons to move freely. Before that point, ordinary light remained trapped inside dense plasma. Electromagnetic observation cannot penetrate earlier. Gravitational waves can. A primordial gravitational wave background, often called the stochastic background, could preserve information from fractions of a second after the beginning itself, potentially even from inflation. Instead of observing ancient light, we would observe ancient space-time motion directly. Hints may already exist. In 2023, multiple pulsar timing array collaborations announced evidence for a low-frequency gravitational wave background permeating the cosmos. Pulsars, rapidly rotating neutron stars emitting regular radio pulses, function like extraordinarily precise galactic clocks. Tiny disruptions in pulse timing across many pulsars suggest gravitational waves passing between Earth and the pulsars themselves. The source remains uncertain. Supermassive black hole mergers likely contribute significantly. But some researchers continue exploring whether part of the signal could originate from extremely early universe physics tied to inflation or cosmic phase transitions. Future observatories may sharpen the picture dramatically. The European Space Agency approved LISA, the Laser Interferometer Space Antenna, for launch during the 1930s. Instead of 4-kilometer arms, LISA will use 3 spacecraft separated by approximately 2.5 million kilometers, forming a vast, triangular detector orbiting the Sunday, sensitive enough to hear ancient spacetime itself. Different inflationary models predict different gravitational wave signatures. Some produce stronger primordial backgrounds. Others leave distinct frequency distributions. If LISA detects those patterns clearly, physicists may finally distinguish among competing models of cosmic inflation. For the first time, humanity may not only observe the early universe, we may listen to it directly. There is a quiet misconception hidden inside almost every image of the cosmos. When we say the universe is 13.8 billion years old, it feels natural to imagine a sphere with a radius of 13.8 billion light-years. But the universe did not remain static while light traveled through it. Space itself kept expanding during the journey. So the observable universe is far larger. The most distant light we can currently detect began traveling toward us shortly after the early universe became transparent. Yet the regions emitting that light are now approximately 46.5 billion light-years away in every direction. And that distance keeps increasing. Inside this observable region lies an almost unmanageable number of structures. In 2016, astronomers analyzing deep field observations revised the estimated galaxy count dramatically upward. Earlier estimates suggested roughly 200 billion galaxies, but faint populations invisible to previous surveys implied a much larger figure, closer to 2 trillion galaxies. Each galaxy contains millions, billions, or even trillions of stars. Combined estimates place the total stellar population of the observable universe near 1 septillion stars, around 10 to the 24th power. That number exceeds all grains of sand across Earth's beaches and ocean floors by roughly 10,000 times. Yet the universe is not evenly scattered. Matter arranges itself into what cosmologists call the cosmic web, a gigantic filamentary structure spanning unimaginable distances. Galaxy clusters gather along luminous filaments and dense walls, while enormous voids separate them. Some of those voids stretch hundreds of millions of light-years across, containing almost nothing at all. Gravity shaped this architecture slowly. Dark matter guided the process, pulling ordinary matter into denser regions over billions of years. What emerged resembles a neural network more than a random distribution, vast strands connecting islands of galaxies across the darkness. Some structures appear disturbingly large. In 2013, astronomers studying gamma-ray bursts identified what became known as the Hercules Corona Borealis Great Wall, an immense concentration of galaxies spanning roughly 10 billion light-years. Its scale challenges the cosmological principle, the assumption that the universe becomes statistically uniform at sufficiently large distances. Because structures this large should not exist easily within standard models. But even these immense formations occupy only the observable portion of reality. The observable universe is not the entire universe. It is simply the region from which light has had enough time to arrive since cosmic expansion began. Beyond that boundary, space continues, possibly forever. An infinite universe produces consequences stranger than fiction. The number of possible quantum arrangements inside a finite region is itself finite. Matter can only organize in so many ways. In an infinite cosmos, those arrangements eventually repeat. Not metaphorically, literally. Some calculations suggest an identical configuration to our observable region would statistically recur at distances around 10 raised to the power of 10 to the 28th meters. Beyond comprehension, beyond visualization, another Earth, another you, another conversation unfolding beneath different stars, or infinitely many variations. And against that scale, every deep field image captured by Webb changes character completely. Every ancient galaxy, every anomaly, every faint red arc suspended in darkness, becomes something unexpectedly small. A single fragment inside a structure so immense that ordinary language no longer survives intact. For most of modern cosmology, the universe's ending appeared strangely quiet. Under the standard Lambda-CDM model, expansion continues forever. Galaxies beyond our local group drift steadily away until their light can no longer reach us. Over trillions of years, star formation slows as galaxies exhaust their cold gas reserves. Existing stars fade gradually, leaving behind white dwarfs, neutron stars, and black holes. Then darkness deepens further. Even black holes are not eternal. Stephen Hawking showed in 1974 that quantum effects near the event horizon allow black holes to emit faint thermal radiation, now called Hawking radiation. Across incomprehensible timescales, even supermassive black holes slowly evaporate into empty space. The largest require around 10 raised to the power of 100 years. After that, only diluted particles remain scattered across an expanding cosmos approaching maximum entropy, a state of thermodynamic equilibrium where no usable energy gradients survive. Cosmologists call this heat death, a cold ending, silent and final. But this picture depends entirely on one assumption, that dark energy remains constant forever. If DESI and future observations confirm otherwise, the fate of the universe changes immediately, possibly dramatically. One possibility is weakening dark energy. In that scenario, expansion gradually slows as gravity regains influence over cosmic scales. Galaxies stop receding as quickly. Over immense spans of time, expansion halts completely and reverses. The universe begins collapsing inward toward increasing density and temperature. A big crunch. Some cyclic cosmologies go further, proposing that such a collapse does not end existence, but triggers another expansion phase, another Big Bang emerging from the compressed remains of the previous cosmos. An eternal sequence. But dark energy may evolve in the opposite direction. If its strength increases over time, the universe approaches what physicists call the Big Rip. Expansion accelerates until gravitationally bound systems fail. Galaxy clusters separate first, then galaxies themselves unravel. Later, stellar systems lose cohesion as planets drift away from their stars. Eventually, atoms cannot survive. If expansion becomes sufficiently violent, even electromagnetic forces are overcome. Electrons detach from nuclei. Matter dissolves into isolated particles. In extreme versions, nuclear forces themselves fail, tearing apart protons and neutrons. All structure ends at a finite moment. Current measurements suggest such an outcome, if real, lies no sooner than roughly 16 billion years ahead, but observations have not ruled it out. There is another possibility still. Dark energy may oscillate, strengthening and weakening across cosmic time. The universe could alternate between periods of expansion and contraction indefinitely, generating cycles of structure without permanent beginning or end. But beneath all these scenarios lies something stranger. The Higgs field, the quantum field giving particles mass, may not occupy its true lowest energy state. Physicists call this metastability, a condition similar to a ball resting temporarily in a shallow valley rather than the deepest one available. If a quantum fluctuation triggered transition into the true vacuum, physics itself would reorganize instantly. A bubble of altered laws would expand outward at light speed, rewriting every interaction it touched. No warning would arrive first, because information cannot outrun the boundary. the probability appears extraordinarily small. Yet across infinite time, even rare possibilities become unavoidable eventually. And so, the universe's future now hangs on measurements. Humanity is still refining, equations still incomplete, and a form of energy we still do not fully understand. Somewhere inside the numbers, there should be company. The observable universe contains roughly 2 trillion galaxies. Each galaxy holds millions or billions of stars, and over the past 3 decades, astronomers have confirmed that planets are not unusual accidents. They are common outcomes of star formation. The Milky Way alone may contain hundreds of billions of planets. Many orbit within habitable zones, regions where temperatures allow liquid water to exist on planetary surfaces for immense spans of time. Chemistry has time there. Complexity has time there. Evolution has time there. So the silence becomes difficult to ignore. In 1961, astronomer Frank Drake proposed a framework for estimating the number of detectable civilizations in our galaxy. The Drake equation does not produce one answer. It organizes uncertainty into measurable categories: star formation rates, the fraction of stars with planets, the probability of life emerging, the likelihood of intelligence, and the lifespan of technological societies. Under optimistic assumptions, the equation predicts millions of active civilizations in the Milky Way alone. Yet after more than 60 years of SETI, the search for extraterrestrial intelligence, humanity has confirmed nothing: no verified transmissions, no engineered structures, no unmistakable evidence that another civilization has ever spoken across interstellar space. This contradiction became known as the Fermi paradox. Physicist Enrico Fermi summarized it with unsettling simplicity. If intelligent life should be common, where is everyone? The paradox has only intensified as astronomy improved. Webb now studies exoplanet atmospheres directly, using spectroscopy to separate incoming light into its component wavelengths. Molecules absorb specific wavelengths, leaving chemical fingerprints inside the spectrum. For the first time, we can examine alien air. In 2023, Webb detected carbon dioxide in the atmosphere of K2-18b, a sub-Neptune world approximately 120 light-years away. More controversially, researchers also reported a possible dimethyl sulfide signature. On Earth, dimethyl sulfide is produced almost entirely by marine microorganisms. The signal remains disputed. Additional observations are required, but even tentative detection marks a turning point. We are approaching the threshold where biology itself may become observable across interstellar distances. But the larger silence remains. One explanation is called the Great Filter. Somewhere between dead matter and galaxy-spanning civilization lies a barrier so difficult that almost no species pass through it. Perhaps complex life is extraordinarily rare. Perhaps intelligence usually collapses into extinction before achieving long-term survival. Or perhaps technological civilizations destroy themselves. The terrifying question is whether the filter lies behind us or ahead of us. If it lies behind us, then humanity may already be unimaginably fortunate. But if it lies ahead, then every silent sky becomes a warning from civilizations that reached our stage and failed to continue. The multiverse changes the emotional geometry of the paradox slightly. In an infinite landscape of universes, life may flourish endlessly, beyond causal boundaries we can never cross. But inside our own universe, the numbers remain immense, the silence remains measurable, and the absence of evidence continues pressing quietly against the darkness between the stars. Long before telescopes reached orbit, before Webb unfolded beyond the moon's distance, humanity discovered something quietly astonishing. The universe behaves mathematically, not loosely, not symbolically, with extraordinary precision. The orbit of planets, the decay of atoms, the bending of light near gravity, the vibration of quantum fields, all of it follows mathematical relationships that can be written on paper long before observations confirm them. Again and again, the equations arrive first. Then reality follows. Quantum electrodynamics, the quantum theory describing interactions between light and charged particles, predicts the magnetic moment of the electron with accuracy extending to 12 decimal places. Experimental measurements match those predictions to the same precision. Nothing else in human knowledge approaches this level of agreement. In 1960, physicist Eugene Wigner published a paper with a title that became famous across science: The Unreasonable Effectiveness of Mathematics in the Natural Sciences. His question was simple and deeply unsettling. Why should abstract mathematical systems invented inside the human mind describe external reality so perfectly? There is no obvious reason they should. Numbers, geometries, and equations began as conceptual tools, yet somehow they map directly onto the structure of existence itself. Differential equations describe gravity. Complex numbers govern quantum mechanics. Tensor calculus predicts black holes decades before telescopes observe them. Again and again, mathematics reaches beyond observation, sometimes frighteningly far. This mystery led physicist Max Tegmark to propose one of the most radical ideas in modern cosmology, the mathematical universe hypothesis. Under this framework, mathematics does not merely describe reality. It is reality. According to Tegmark, every mathematically consistent structure exists physically somewhere. Universes with different dimensions, different laws, different particles, all realized as valid mathematical forms within an enormous multiverse of possible realities. The proposal sounds philosophical at first, but it emerges from a practical observation. If every consistent mathematical structure exists, then physical constants no longer require explanation. There is no special tuning problem because every arrangement occurs somewhere. We inhabit one compatible with observers. But many physicists resist this conclusion. To them, mathematics may simply be the language most capable of modeling the universe rather than the substance composing it. Somewhere beneath the constants and symmetries may exist a deeper equation forcing reality into exactly one possible form, a final law. Albert Einstein spent the last 3 decades of his life searching for such a framework. He hoped for a unified field theory, one mathematical structure merging gravity and electromagnetism into a single coherent description. In principle, such a theory would make the universe inevitable rather than contingent. He never found it. Neither has anyone else. Modern physics remains divided between 2 possibilities. Either reality could have been otherwise, requiring some selection process among countless possibilities, or the laws could only exist exactly as they are, fixed by a deeper mathematical necessity still hidden from us. But whichever possibility proves correct, mathematics occupies a strange position within the cosmos. It appears simultaneously invented and discovered, created by minds that themselves emerged from the very universe those equations describe. And somewhere in that loop, physics approaches a boundary where observation fades into interpretation, where equations stop behaving like tools and begin resembling the underlying architecture of existence itself. Imagine discovering that our universe is not the system, only a sample. Under eternal inflation, space never stopped generating new regions of reality. Inflation ended locally inside separate bubbles while continuing elsewhere indefinitely. Each bubble became its own universe, expanding with distinct initial conditions and potentially different physical laws. Not one cosmos, countless. If this picture is correct, then every physically consistent universe exists somewhere across the larger inflationary structure. Universes with stronger gravity, universes with no stable atoms, universes where stars burn blue for trillions of years, universes sterile and dark from their first moments, and universes astonishingly similar to ours. This changes something deeper than astronomy. For centuries, science steadily displaced humanity from privileged positions. Copernicus showed Earth was not the center of the solar system. Later discoveries revealed the Sun was one ordinary star among hundreds of billions inside the Milky Way. Then the Milky Way itself became one galaxy among trillions. But the multiverse extends the demotion further still. Our universe may not occupy a central role either. Its laws may not be universal laws in the absolute sense, only local conditions inside one habitable bubble among an uncountable number. The strength of gravity, the mass of the electron, the density of dark energy, these may resemble atmospheric conditions more than eternal truths, specific to where we emerged. The consequences reach directly into the fine-tuning problem. Hydrogen persists for billions of years because the strong nuclear force falls within a narrow range. Carbon forms because nuclear resonances align with remarkable precision. Chemistry functions because electromagnetism possesses exactly the right strength for stable atoms and molecular bonds. Inside a single universe, these conditions appear improbably precise. But inside a multiverse containing every viable arrangement, improbable combinations inevitably occur somewhere. Observers naturally emerge only within the rare regions compatible with complexity, chemistry, and long-lived stars. We should expect to find ourselves in one. Some physicists consider this deeply unsatisfying. The universe loses its apparent uniqueness. Existence begins feeling statistical rather than purposeful. One successful configuration selected not by design, but by sheer numerical inevitability. An accident among infinities. But others react differently. They argue that probability does not diminish wonder. Out of all possible physical arrangements, one produced galaxies, oceans, language, memory, mathematics, and nervous systems capable of reconstructing cosmic history from photons crossing billions of light years. That remains extraordinary, perhaps even more so, because the multiverse does not erase meaning automatically. It only removes the assumption that meaning must originate from rarity. A sunset is not less beautiful because sunsets occur elsewhere. Consciousness is not less profound because consciousness may arise repeatedly across reality. But physics cannot settle that argument. It can describe inflationary fields, map cosmic background radiation, and calculate probability distributions across hypothetical universes. It can carry us astonishingly far into the structure of existence. Then it stops. At the boundary where equations end and interpretation begins, the question of what any of this means no longer belongs entirely to cosmology. It belongs partly to you. Long before the first infrared image arrived on Earth, The telescope already existed in fragments scattered across laboratories, clean rooms, simulation chambers, and meeting tables spread across continents. It began as an argument about whether humanity should attempt something this difficult at all. The James Webb Space Telescope required 25 years of development, more than 10,000 engineers and scientists, and collaboration across 14 countries. By the time it launched in December of 2021, the cost had reached approximately $10 billion, making it the most expensive scientific instrument ever sent into space. And still, cancellation remained close. In 2005, funding concerns nearly halted development before the telescope's final architecture was complete. In 2011, the United States House Appropriations Committee proposed terminating the project entirely after budget overruns and repeated delays. Then again, in 2018, mounting technical complications reopened doubts about whether Webb would ever fly. But astronomers kept defending it, not because they knew what Webb would discover. No one did. They defended it because the early universe remained hidden behind wavelengths older telescopes could barely reach. Somewhere beyond those limits were answers connected to galaxy formation, dark matter, inflation, and the structure of cosmic history itself. Questions large enough to justify risk. The deployment sequence alone bordered on impossible. Webb launched folded inside an Ariane 5 rocket, compressed like delicate machinery, packed into impossible geometry. Once in space, 344 separate mechanisms had to activate correctly in exact order. Hinges rotated, latches released. Motors tightened membranes thinner than human hair across the length of a tennis court. One major failure would have ended the mission permanently. No astronaut could repair it. The telescope traveled toward Lagrange Point 2, 1.5 million kilometers from Earth, carrying decades of human work beyond physical reach. During those first weeks after launch, teams monitored every unfolding step in near continuous shifts. Engineers slept beside laptops. Scientists refreshed telemetry feeds through the night, waiting for confirmation signals. Bill Ox, Webb's project manager, later described how intensely the sequence had been rehearsed before launch. Simulations repeated so often that the team carried the telescope's first month almost instinctively, as if the motions of distant machinery had been memorized directly into muscle memory and nerves. And after all that preparation, the real work only began. The people now analyzing Webb's observations understand something unusual about their position in history. Many of the questions opened by these discoveries may require decades to resolve fully. Careers will end before consensus forms. Entire theories may evolve through generations of scientists who have not yet entered graduate school. Ivo Lebey, whose team identified several of the impossible early galaxies, has spoken openly about that feeling. The discoveries did not feel complete. They felt unfinished, almost burdensome, like receiving a calculation whose consequences extend beyond a single lifetime. But this has always been the rhythm of frontier science. One generation builds the instrument, another interprets the anomaly, a later one understands what the anomaly meant. Meanwhile, Webb continues observing in silence. New photons continue arriving from the edge of visible time. Somewhere inside those incoming streams of data, another contradiction is already waiting to be noticed. Before the Earth existed, before oceans formed or continents cooled, ancient stars were already living brief, violent lives in galaxies, now visible through Webb's mirrors. Their light is only arriving now. Some of the photons entering the telescope today began their journey more than 13 billion years ago, crossing expanding space long before the sun ignited roughly 4.6 billion years in the past. When those photons departed their galaxies, the Milky Way did not yet exist in its present form. The atoms that would eventually become Earth were still scattered across older stellar systems, drifting as ash inside interstellar clouds. Nothing recognizable as us existed yet, and still, the chain had already begun. The human body is built almost entirely from elements forged inside stars. Carbon forms through helium fusion in stellar cores. Oxygen emerges during later fusion stages in massive stars. Iron appears in the final moments before supernova collapse. Calcium, nitrogen, phosphorus, silicon all passed through generations of stars that lived, died, exploded, and scattered enriched matter back into space. The Big Bang created hydrogen, helium, and traces of lithium. Everything else came later. Over billions of years, gravity gathered those heavier elements into molecular clouds dense enough to collapse into new stars and planetary systems. Around one average star inside one spiral arm of one galaxy, chemistry became sufficiently complex to produce cells, nervous systems, memory, language, mathematics, and eventually, machines capable of detecting infrared light from the edge of observable time. That sequence matters. You are not made from matter preserved, unchanged since the universe began. You are assembled from material, repeatedly transformed by cosmic processes extending across billions of years. Every atom in your blood carries a history older than the planet beneath your feet, and Webb is looking directly into that history. Light from a galaxy observed at redshift 14 left its source approximately 290 million years after the Big Bang. At that moment, the atoms now composing your body were still diffuse particles suspended across regions of space that had not yet formed stars, like the Sunday. The future Earth remained unimaginably distant. But the connection already existed physically. The telescope is not observing something detached from us. It is observing an earlier phase of the same continuous process that eventually produced observers capable of building telescopes. The separation feels enormous because human lives are brief, but cosmically, these events belong to one unfolding structure, one long transformation. Carl Sagan once described humanity as a way for the cosmos to know itself. The phrase endured because it captures something literally true about what is happening when Webb observes the early universe. Through biological evolution, technological civilization, and scientific reasoning, matter arranged itself into forms capable of investigating the conditions from which that matter originally emerged. The universe became observable to itself. Whether the current cosmological model survives this decade or collapses beneath new data, that fact remains extraordinary. In 13.8 billion years of known cosmic history, stars formed, galaxies collided, black holes consumed matter, and space expanded in silence. Then eventually, somewhere inside one small galaxy, awareness appeared. And awareness began looking backward. At the edge of modern cosmology, uncertainty is no longer a temporary inconvenience. It is the landscape itself. The deeper we look into the universe, the less stable our certainty becomes. Each generation of instruments sharpens the image of reality while simultaneously exposing structures our theories cannot fully explain. Precision has not simplified the cosmos. It has revealed how incomplete our understanding remains. The pattern repeats constantly. The discovery of the cosmic microwave background resolved major questions surrounding the Big Bang and the early universe. But embedded inside those microwave fluctuations were new mysteries involving dark matter, inflation, and dark energy. The James Webb Space Telescope confirmed that ancient galaxies exist at astonishing distances, then immediately revealed galaxies forming far earlier and faster than our standard cosmological timeline comfortably permits. Answers create pressure, and pressure reveals cracks. This rhythm is older than modern astronomy itself. In the year 1900, the physicist Lord Kelvin publicly suggested that physics was nearly complete, aside from what he called two small, unresolved clouds on the horizon. Those clouds appeared minor at the time. One involved strange properties of light and thermal radiation. The other concerned the motion of objects through space. Within decades, those problems became quantum mechanics and general relativity. The entire structure of physics transformed. That history matters because it warns us against believing our current frameworks are final. Today, cosmologists can map galaxies across billions of light years, measure fluctuations in the cosmic microwave background to extraordinary precision, and detect gravitational waves smaller than a proton's width. Yet, the foundations beneath those measurements remain partially unknown. We do not know what dark matter is physically made from. We do not know what drives dark energy. We do not know why the constants of nature possess the values they do, or whether those values could have been different. We do not know whether inflation truly occurred exactly as modeled. We do not know whether the multiverse exists beyond theoretical consequence. We do not know what happened before the Big Bang, or whether the concept of before even applies under those conditions. And now Webb has introduced another uncertainty. The impossible galaxies may eventually find explanation within revised formation models. They may reflect unfamiliar behavior in the early universe, hidden properties of dark matter, variations in inflationary conditions, or entirely new physics not yet imagined. There remains the possibility of observational bias or subtle calibration effects. But the larger point survives regardless. These mysteries are not decorative gaps sitting safely at the edge of established knowledge. They occupy the structural center of cosmology itself. They shape every major equation describing the universe's origin, expansion, composition, and fate. The load-bearing walls remain unfinished. History suggests that when problems accumulate at this scale, science does not simply patch the model, it reconstructs it. Copernicus displaced Earth from the center. Einstein replaced Newtonian gravity with curved spacetime. Quantum mechanics overturned classical certainty at microscopic scales. The next transformation may already exist quietly inside Webb's archived datasets, hidden within patterns no one has recognized yet. Or it may require instruments humanity has not designed, observing signals no current detector can measure. For now, we continue mapping reality while standing inside questions larger than ourselves. And perhaps that has always been the true condition of science. At the beginning of this journey, we looked toward a tiny region of darkness, a patch of sky so small it could disappear behind a grain of sand held at arm's length. Inside that narrow window were thousands of galaxies. Some appeared ordinary. Others arrived carrying a problem large enough to unsettle modern cosmology itself. Ancient galaxies emerged too bright, too massive, too organized for the timeline our equations predicted. The farther Webb looked, the less comfortable the old assumptions became. And from that discomfort, the story widened. A cosmological model, refined across more than 50 years, suddenly faced observations it could not easily absorb. The chain of reasoning stretched outward from impossible galaxies to inflation, from inflation to eternal expansion, from eternal expansion to the possibility that our observable universe may be only one region inside something vastly larger, possibly infinite. Along the way, we encountered dark matter, which shapes galaxies without ever revealing its identity directly. We followed dark energy, the unknown pressure accelerating cosmic expansion while resisting explanation. We arrived at fine-tuned constants, balanced so precisely that slight changes would erase stars, chemistry, or stable matter entirely. Every path led toward deeper uncertainty. But uncertainty is not failure. It is evidence that reality still extends beyond the edge of our understanding. The data gathered by Webb is real. The Hubble tension is real. The questions surrounding inflation and dark energy are real. Whether the eventual explanation involves revised galaxy formation, new quantum fields, changing dark energy, or entirely unfamiliar physics, something important is being exposed. A boundary has been reached. History suggests this is where science changes shape. Every generation that examined the universe closely enough discovered that previous certainty had been incomplete. Earth was not the center of creation. The Milky Way was not the only galaxy. Space and time were not fixed backgrounds. Matter itself was not solid or deterministic, in the way earlier physics imagined. Each discovery expanded the scale of reality. There is no reason to assume the expansion has stopped with us. The cosmos existed for 13.8 billion years before human beings learned to build telescopes. It endured through epochs of darkness, stellar birth, galactic collision, and silent expansion long before any living creature could observe it. One day, long after human civilization disappears, stars will continue burning across distances too large for language to hold comfortably. The universe does not depend on being understood. And still, for a brief moment inside that immense history, matter organized itself into minds capable of asking what all this is. We built instruments from metal, silicon, mathematics, and patience. We launched them into darkness. Then we waited for ancient light to return. The same photons that challenged cosmology are still traveling tonight. The same distant galaxies continue drifting through expanding space. If inflation never truly ended, then somewhere beyond every observable horizon, space-time may still be unfolding into regions no signal from Earth will ever reach. All of it remains out there now, so you can let the questions rest for a while. The universe has carried them far longer than we have.